Hi, my name is Osman, and I'm presenting our work Auto-Vocabulary Semantic Segmentation, accepted at ICCV2025. This was a joint work with Maximilian, Yuki, and Martin. We motivate our work as an advancement on fixed set user-specified open vocabulary segmentation. In these types of models, a human needs to be in the loop, the predictions will only span the provided vocabulary, the semantic specificity of the predictions will be limited to the fixed vocabulary, and if new classes appear, it will require the user to update the vocabulary. To give an example, imagine a kitchen robot that needs to distinguish a large variety of tools and ingredients when cooking a recipe. It is undesirable to require a human-provided prompt for every grasp or to relabel a dataset and retrain the segmentation method every time a new recipe contains a new tool or ingredient. Likewise, in autonomous driving, we want the car to be able to recognize all potential objects it might ever encounter on the road that could cause a dangerous situation. To indicate all possible classes in the world with an OVS approach would simply be unrealistic, as it would require us to list thousands of classes that are continuously being updated. In contrast, auto-vocabulary semantic segmentation is automatic, it is scene-specific, and it has an open-ended vocabulary. It is more semantically precise with regards to the classes, and it is scalable because no relabeling is required. To tackle auto-vocabulary segmentation, we propose AutoSeg. AutoSeg first encodes the image into patches using a pre-trained BLIP vision language model. As you might know, BLIP has both an encoder and decoder, which allows it to caption the image itself. However, usually such captions will focus on the most salient objects, which yields an unsatisfactory level of vocabulary completeness for a per-pixel task like segmentation. Hence, we enhance non-salient object locality in embeddings with BBoost through semantic clustering, cluster alignment, and denoising of those clusters. After BBoost, AutoSeg decodes the now enhanced embeddings into captions with BLIP's original decoder and filters these captions into a noun-level vocabulary. The generated auto-vocabulary is then used by a segmenter to output the final segmentation. For evaluation, we map auto-generated open-ended classes to known dataset classes using LAVE. This step is important to examine the performance of the method in relation to the known annotated classes. Our main module, BBoost, has three main components: clustering, alignment, and denoising. In the clustering step, we cluster BLIP patch embeddings with k-means clustering at 2 image resolutions. We run k for a range of different values, which results in semantic clusters at different granularities. This process supports multiple cycles of the same procedure for robustness, as each clustering cycle can result in different semantic clusters for the same image. The second step is intended to unify the cluster assignments of k-means that we just ran for different values of k into one representation. Using feature-based Hungarian matching, we match semantic clusters with each other across different runs and aggregate them into consistent soft-cluster assignments. In the final step, we remove any noisy patches that influence the consistency of semantic clusters as a result of the preceding 2 steps. For this, we use a conditional random field and neighborhood majority filtering, producing smoother and more coherent semantic groupings. LAVE is a new evaluation protocol for open-ended classes that makes evaluation of AVS feasible and scalable. It leverages an LLM to automatically align novel label predictions with known classes. It will update the masks accordingly to the mapping, and it will compute the MLU without manual class matching. This is one of the outputs of our model on an image of the Pascal VOC set, where the model predicts the breed of the dog rather than just the class dog. The rest of the image is predicted as a bat. To evaluate how well our method is doing, we would need to map these classes to the classes in VOC, which do not include either of the classes. This is how the image would look after mapping. We map the breed of the dog to dog, as it is the closest thing to a dog. And because the bat is not close to anything else in the dataset, it will be mapped to background automatically, ensuring a realistic evaluation of auto-vocabulary predictions. Finally, some qualitative results. Here we see the ground truth annotation of this particular photo, and the next picture is our method's prediction. As we can see, the method classifies the building with the exact type of building. Next, we show 2 pictures that are taken in the wild that actually don't have known annotations. As we can see, our model generalizes well, correctly identifying the mascot and the whole, while never being fed this class. For quantitative results, we refer to the paper. Thanks for watching.